Welcome everyone to this module of ML Summer School. This module is on Supervised Learning Part 3. I am Sandeep Chatterjee, working as an applied scientist in Amazon Sciences for the RBS Tech team. The agenda of this module is learning about decision trees and ensemble learning. Then we will go with multi-class classification, class imbalance problem, and cross-validation methods. Next, we have hyperparameter tuning and model selection. Lastly, we have probability calibration and hands-on demo on all these. So let's start with decision tree and ensemble learning. Starting with decision trees, what are decision trees? So the fundamental idea here, as you can see on the slide, is to recursively partition our feature space using simple if-then rules. In plain English, a decision tree is just a flow chart. At every single step or node, the model asks one specific question about one specific feature to split the data. Let's look at the flowchart figure given here. Imagine we are trying to predict whether to give loan to a customer or not. So we start at the top, the root. The first question the tree asks is the person's age 30 or younger? If yes, we go left. If no, we go right. It then asks follow-up questions like for the left part, is their income less than or equal to 50K? Or if the age was not less than 30, then we ask, do they own a home on the right part? So so likewise, we keep splitting until we reach the bottom. So these bottom are called leaf nodes. So these are our leaf nodes, and this is where the model finally makes a confident prediction, classifying each data point either into class A or class B. So this was all about what decision trees are. We are going into why behind the splits. Now, looking at this flowchart, a crucial question should pop up into our mind is how does the tree know which question to ask first? Why did it ask about age instead of income at the very top? Things like that. So the tree actually doesn't just guess, it relies on math, and it wants to ask the question that best separate our mixed up data into pure distinct classes. So the algorithm involves a measurement of what we call as splitting criteria. So let's break down the math. We will go through few metrics. So our first metric is Gini impurity. So it is very simple. The formula is 1 minus summation of pi square for all I. So this is a impurity metric. So think of impurity as how mixed up our data is. So if you randomly label the data point based on the distribution in the node, your chance of making a mistake will be more if you have impure data. So if a node is completely pure, meaning every single person in that group belongs to just one class, let's say class A, the Gini score is exactly 0, and you can convince yourself with usage of calculus or some other mathematical methods, and this will be maximized. This Gini will be maximized for two classes if pi is 0.05. So in that case, the group will have perfect 50-50 split. So this is maximized when actually both the classes are balanced. So if you have 50-50 split of class A and class B, the Gini score hits the maximum of 0.5. And in that case, the data set will be maximum impure. This is what Gini impurities. And we have an alternative, which is actually better metric. This is known as clouds and an entropy, or we simply say entropy, which comes from the information theory. So the formula looks like this. H is summation of pi log pi in base 2 for all I, summation for all I, and this is negated. So this is better, but the reason we use Gini is because entropy involves computation of log with floating point log in base 2, while in Gini we simply need square. So but entropy is a better measure, and just like with Gini, a perfect pure node will have an entropy of 0, and a highly mixed node has high entropy. Entropy is measured in bits, and it's essentially a measure of disorder or chaos in our data. So a tree's job will be to bring order to the chaos. We will need maximum order, minimum chaos. And so how does the tree actually evaluates a potential split? Is that it uses information gain. So information gain is our next metric, which is yeah. Which is entropy of parent minus weighted average entropy of the child, which is like entropy of before minus the sum of entropies in the after. Yeah. So which is entropy of parent minus weighted average entropy of the child, which is like entropy of before minus the sum of entropies in the after. So when the tree is deciding its next move, it looks at the every possible question it could ask, and it calculates the information gain for each one. So information gain, as we saw, is simply the impurity of our parent node minus the weighted average impurity of the child nodes of the after the split. So the question that results in the highest information gain, the one that reduces our chaos the most, is the winner. All right, so now we understand the logical math behind how decision tree builds themselves, and while inference, we just traverse the tree and make the decision. But in applied machine learning, no algorithm is a silver bullet. So let's talk about the practical reality, the good part, the bad part, and how we keep them under control. So the strengths of decision tree of why we love them is the absolute biggest advantage of the decision tree is strictly interpretability. So if you build a complex neural network, the network as a whole, it's a black box. But with a decision tree, you can print the flowchart, walk into a meeting with business stakeholders, and explain exactly why the model made a specific prediction. So if you have a prediction of data point, you have the exact traceability. You know which rules were followed to infer this prediction, and as well as you also know the exact threshold of why a rule was triggered or exact threshold of why a rule was not triggered. So this is the good part. The next part is they are also incredibly low maintenance. So unlike many other many other algorithm, decision tree can handle mixed data type natively. So you don't need to scale or normalize your features beforehand. And because they use those hierarchical splits, they naturally capture non-linear relationships. So no scaling is needed, and it captures non-linearity very well. Now, coming to the weaknesses, the dark side of trees is that decision tree are often prone to overfitting because they are so flexible, they have high variance. And this means if you just change a tiny handful of data point in your training set, the math might cascade very differently, and it will end up with very different, wildly different tree, which will have different predictions. So because if they are left to their own devices, they will grow until they perfectly memorize the training data. So this perfectly memorizing is what we call as overfitting, because it will include all the random noise, which means they will fail terribly in the real world. They might perform very well in the training data, but in the real world, they will fail terribly. So this is one weakness. Another terrible weakness is greedy splitting. So remember how we talked about the information gain. So at each step, it is only looking at the best possible split for that exact moment, the next moment. So it does not plan ahead because it's only optimizing locally at each node. It might miss out on globally optimal tree structures. So it quite literally cannot see the forest for the trees in the future. So these was the weaknesses. Now, how do we control this? So control overfitting, we stop. How do we stop them from memorizing the noise? So we have to set some boundaries using some hyperparameters. So what we can do is we can set a max depth. Again, we can use mean sample split or mean sample leap to enforce a rule that says you are not allowed to make a new split unless you have at least 50 data point in this node. Because if you have less data, that is not very much representative, and you are not very much confident with that rule. Alternatively, you can also let the tree grow completely wild, then use a technique called tree pruning. So it's called pruning. Specifically, it is about cost complexity reducing. So in this, we go backward and chop off the specific branches that do not actually add much predictive power. So to wrap up this, when you should actually reach for a decision tree in your project is when interpretability is a hard requirement. You can use them when you are working with standard tabular data with a mix of feature, and they are fantastic for feature important analysis, giving you a quick baseline understanding of which variables in your dataset actually matter before you move on to building more complex models. So the wrap up, brilliantly good for interpretability, but they will suffer from high variance, and you can exactly know how they make the decisions. But if you do not keep them on a leash, they will overfit your data. So to make them actually useful in real world setting, you have to control their variance, setting boundaries like max depth or pruning. All right, we have covered the math, the strengths, and the weakness. To summarize, decision trees are brilliantly interpretable, but they suffer from high variance. That's why you have to control them with setting boundaries. But here is one thing. Uh, a single decision tree is rarely used on its own in modern large-scale machine learning systems. Instead, they are fundamental building blocks. So decision tree truly shines when you combine hundreds or thousands of them together into what we call as ensembles. So that's our next topic. We use ensembles like random forest or gradient boosted trees. So all right, let's dive into some of the most practical aspects of using decision trees, starting with feature importance. So when you throw a massive data set at a decision tree with dozens of features, you usually want to know which of these features actually drove the predictions. The tree calculates this by looking at the total impurity reduction across all the splits where a specific feature was used. So intuitively, the features used higher up in the tree, closer to the root, have the biggest impact because they are separating the largest chunks of the data very early. So if you are coding this up in Python, scikit-learn makes it incredibly easy. You just call tree.feature importance, and it gives you an array of scores neatly normalized to sum to 1, telling you exactly how uh, valuable each feature was, the exact weightage. So to make sure we completely grasp the math we talked about earlier, let's look at the Gini impurity with some quick numeric intuition. So imagine a node where our data is perfectly split down the middle, a 50-50 split of class A and class B. So if we plug that into our Gini, we get this is the maximum impurity. This is our worst case scenario where our data is maximum impure. So it's the maximum impurity. So essentially a coin toss, it's like a coin toss where you cannot bet on either head or tell if your coin is unbiased. Now, what if the tree makes a great split? We can end up with, let's say, in that case, your Gini impurity will be 0.18. You can see the impurity drops significantly, right? Because it's mostly pure now. So it will result in a zero impurity. It's a perfect score. So, and this will happen in either way. So if it is 100 zero split or 0 100 split, it is the same. So like it should be that all data points are in one class. It doesn't matter which class. So this is a perfectly pure leaf node where the model is 100% confident. Now, talking about pruning strategies, we have pre-pruning to prevent from memorizing the noise. So how do we do it? We prune it. And there are two main ways to do it. First is pre-pruning. So this is where you set the ground rules before training even begins. So you tell scikit-learn things like do not grow trees deeper than max depth of 5. So or you can have rules like every leaf must have min samples leaf of at least 20. So it stops the tree from over expanding in the first place. Second is post pruning. So specifically it is about cost complexity pruning. So here you let the tree grow as deep as it wants. Then you just use a parameter called CCP alpha. So to penalize complexity. So you evaluate the tree and systematically snip off the weak branches at the bottom where tiny gain in purity. So a higher CCP alpha means more aggressive pruning. So to wrap this all up, remember that individual trees are essentially building blocks, but a single tree will have very high variance and will be a weak predictor. But they are essential foundations for powerful ensemble method. And why all of this matter in real world is, let me give you a quick example from right here at Amazon. Imagine we are trying to do a root cause analysis RCA on delivery delays. So we could use a complex deep learning model to know when to expect a delay. So our operations team would know what to do with it, right? Instead, with complex model. So instead, we can use a decision tree. The model output will be highly interpretable rules. So it may say something like if weather is heavy rain and distance is more than 50 kilometer, then predict delay. So that is a clear actionable insight that an operations manager can instantly understand and use to improve our network. So that is the true power of an interpretable model. And decision tree are highly interpretable model. So our next topic is ensemble learning. So here, instead of relying on one super complex model that might overfit, as we saw with decision trees, we combine multiple weak models to create one massive, strong model. So that wisdom of the crowd is exactly what we are building here. So let's start with bagging. The most common way we build this crowd is through a technique called bagging, which stands for bootstrap aggregation. So here is how it works. Instead of training 100 trees on exactly same data set, which would just give us 100 identical trees of no use, we create bootstrap samples. This means we sample our original data with replacement. So every tree gets a slightly different randomized version of the data set to train on. Once all these trees are trained, we aggregate their predictions. This is for combine. So if we are doing classification, we let the trees vote and take the majority. And if it's a regression, we take the average. The mathematical beauty of bagging is that it directly attacks a decision tree's biggest weakness, which is it heavily reduces variance without increasing the underlying bias. Uh, the upgraded version is random forest. So random forest take bagging and add one brilliant twist. So what if all our trees look at the exact same features? They might still make very similar decisions, right? Especially if one feature is super dominant. They become correlated. So to fix this, a random forest forces the tree to look at random subsets of features at every single split. So for classification tasks, a single standard rule of thumb is to give each split access to the square root of the total features. For For regression, it's about a third. So by restricting the features, we decorrelate the trees. So this is about how do we tune the forest. So let's look at three key hyperparameter. First one is n estimator. So this is about how many trees we are using. This is just the number of trees. So the great news here is you literally cannot overfit by adding more trees to a random forest. You will eventually hit diminishing returns and waste compute power. But it is generally perfectly safe to increase the number. Now, next is max features. So if you lower this, you force more decorrelation. So your trees become more diverse, which lowers variance, but it might also introduce a tiny bit more bias. So it will have less variance, but more bias. That's why you have to balance this. Next one is max depth. So unlike single decision trees where we have strictly limit depth to prevent overfitting, yeah, what it means in a random forest is we often let the trees grow much deeper. So we want them to have low bias because the bagging process across hundreds of tree will naturally compensate for the high variance. So we can close this with the final topic called out of bag or OOB score. So because how we sample our data with replacement, roughly 30% of the original data gets left out for any given tree. So this algorithm uses this unseen data to validate the tree on the fly. It's essentially a free built-in validation set without having to hold out a separate data. So to summarize, when should we use random forest? It should absolutely be your default go-to starting point for any tabular data problem. It makes very few assumptions about your data. It's incredibly robust to outliers. And because every tree is independent, you can easily parallelize the training across multiple cores. Now, coming to the next topic, we have boosting. So the core idea behind boosting is instead of training models in parallel, we train them sequentially. So every single tree is in the sequence has one specific job to look at the mistakes made by the tree right before it and correct them. The logic is highly intuitive. When the first tree makes its prediction, it will inevitably get some samples wrong, right? So AdaBoost take those misclassified hard examples and literally increases their weight in the dataset for the final scoring. So when the second tree is built, it is forced to pay far more attention to those heavily weighted difficult examples. So, and it repeats this process, chaining together all the weak learners and giving them a weighted vote. However, because it obsesses over misclassified points, it can be quite sensitive to noisy data or extreme outliers. To make this process more robust, we shifted to gradient boosting. So instead of just changing sample weights, gradient boosting uses calculus. So each new tree in the sequence is trained to predict the residual errors of the previous model. So think it of like playing golf. Your first shot gets you close to the hole. Your next shot is just trying to cover the remaining distance, the residual error. So mathematically, it builds an additive model that looks like this. So your fx is sum of all alpha m multiplied by h of m of x. So this means our final prediction is sum of all the individual trees scaled by a learning rate. And because each tree is doing a tiny bit of error correction, we keep them shallow, usually just a depth of 3 or to maximum of 8. So and then there are in heavyweights algorithm, for example, XGBoost, LightGBM, and CatBoost. So now if you want to win a Kaggle competition or deploy a world-class tabular model, here at Amazon, this is the section you care about. XGBoost, Light, BGM, CatBoost, they're heavily optimized state-of-the-art implementations of the gradient boosting. So why are they so dominant? Because they are incredibly fast. They parallelize the way they find splits, unlike the previous algorithms. Here you have to be careful while tuning them. So remember how we said in the previous topic that you cannot really overfit a random forest by adding more trees, right? Boosting is the exact opposite. So because it sequentially chases errors, if you increase n estimators too much, the model will eventually memorize the noise. So a lower learning rate will mean the model will learn slower and is more regularized. But you will need more trees to reach good performance through its iterative sequences, not by growing massive individual trees. Here is your final key takeaway for tree-based model that unlike random forest, sequential trees fit residuals. They reduce both bias and variance simultaneously. And if you are working with tabular data in the real world, algorithms like XGBoost and light BGM should be your absolute defaults. But because they are so powerful and prone to over optimizing, you must always pair them with early stopping, a technique that monitors the validation error and automatically halts training. So you have to master these concepts, then you will have one of the most powerful machine learning algorithms in the industry at your fingertips. Now coming to the next topic of bagging versus boosting and when to use what. So let's look at the bagging first, with random forest being our prime example. The defining characteristic here is parallel training, because every tree is completely independent of the others. You can easily distribute the training across hundreds of machines. It's fast and highly scalable. Its main job is to reduce variance. Because of that wisdom of the crowd effect, it has an incredible low risk of overfitting. If a few data points in your set are completely wrong, the random forest generally won't care, because the majority vote drowns out the errors. So when is this your go-to? You reach for a random forest when you are dealing with a high variance based learner, and when your data is a bit messy or noisy, and when you absolutely need parallel compute speed. So now contrast that with boosting your XGBoost or LightGBM model. The paradigm completely flips. This is sequential training. So tree number 2 cannot be built until tree number 1 is finished. Tree number 3 likewise cannot be built. So unlike bagging, boosting reduces both bias and variance. But that power comes with a massive catch. It has a high risk of overfitting. So if you do not use early stopping, it will be bad. Furthermore, because boosting is literally designed to obsess over misclassified examples, it is highly sensitive to noise. So if you use a garbage outliers in your dataset, the model will upweight them and disparately try to fit to that noise. And when you are willing to spend the time carefully tuning hyperparameters, and when you are absolutely chasing maximum accuracy. In industry competitions and highly optimized production systems, this is usually the winners. To conclude, to summarize, think of random forest like a blunt instrument. It is incredibly robust, easy to swing, and hard to mess up. Think of gradient boosting like a scalpel. So it's far more precise and can achieve better results. But if your hand slips because you did not tune it right, or your data is noisy, so as a quick decision guide for tree-based model, here is how you should think about your workflow. First, when you start a brand new project and your data is a bit messy, or you just need a baseline model running by the end of the day, uh, throw a random forest at it. It's incredibly forgiving. Second, when your data pipeline is pristine and your goal is to squeeze out every single drop of accuracy for a production system, you pivot to XGBoost or LightGBM. That is where you get maximum performance. You have to prioritize interpretability. In those cases, stick to a single decision tree or a random forest where you can easily extract feature importance. And finally, if you are working with any kind of structured tabular data, think like CSVs or SQL databases, spreadsheets. So XGBoost paired with early stopping is simply the industry standard. So lastly, with the right tool and right job, you can apply either bagging or boosting, and you can get the maximum out of it. But both of these dominate basically the tabular data. So if you have something which is outside of tabular data, you have something like multimodality or complex data type. So trees are not the answer for everything. If your data is unstructured like text, or even though it is structured but complex like images or audio, then you have to put the trees away and shift entirely to deep learning or neural networks, where it is seen the with maximum accuracy. So the key takeaway is bagging is for noisy data, for parallelism, variance reduction. Boosting is for clean data, sequential learning, and maximum accuracy. Now, coming to the topic of multi-class classification, class imbalance, and cross-validation methods. So far, a lot of our mental models have been built around binary choices. So, if it is fraud or not fraud, to give loan or not give the loan, will the customer click or not click? But in real world, we rarely have just two options, right? What happens when we need to classify an image into one of 100 different categories, or predict which of our thousands of products a user might buy next? So we need multi-class classification strategies. So let's walk through the three main ways we handle this in practice. So our first way is one versus rest. So this is called OVR, the scalable default. So the most straightforward approach is, let's say we have k different classes. So OVR simply trains k separate binary classification. So if we are trying to identify apple, bananas, and oranges, we train one model that asks, is it an apple or anything else? Another that asks, is it banana or anything else? And so on. So when it's time to make a prediction, we run the data point through all k models, and whichever model shouts the loudest, whichever has the highest confidence score, that wins. That it lets you take almost any standard binary classification and force it to do multi-class work. Our next method is one versus one, the heavy computation. So instead of comparing one class against everything else, we train a dedicated model for every single pair of classes. For example, apple versus banana, apple versus orange, banana versus orange. So now when you have a new data point comes in, all these models vote and the majority wins. So now if you look at the math, you have to train k into k minus 1 by 2. It's like kc2 classifiers. So if you have a massive number of classes, say over 10, these combinatorial explosions become computationally expensive very quickly. So, but why use it? Because each individual classifier is only trained on a small subset of total data. So just the data for the two specific classes. So for example, support vector machines, SVMs, natively scale poorly with large data set sizes due to complex kernel computation. So next is the softmax, which is also the neural network standard. So it is technically multinomial logistic regression. So unlike the previous two methods, which hack together multiple binary classifications, softmax is truly native multiclass. So let's look at the mathematical engine behind this. Uh, the intuition is clear. First, we take the raw output scores of our model. So raw output score is the real number, so it can vary anywhere between minus infinity to infinity. So we apply the exponential function. We raise the score to the power of e. So this one, so this does one critical thing. It squeezes down minus infinity to infinity into 0 to infinity. So it guarantees that all our numbers are positive, no matter what the model outputs as raw score. Secondly, so now all scores are positive. We divide that result by the sum of exponential of all other classes. So this division normalizes the all outputs into fractions between 0 to 1. So it forces every single score to be between 0 and 1, and it forces all the scores to sum up to exactly 1. So in one elegant step, it converts raw arbitrary numbers into clean probability distribution. So uh, next, if you have a small number of classes and you specifically want to use models like SVM, which are not good for very large data set size, so you can use one versus one to save on training time. And if you are building deep learning models or neural networks, softmax will be your standard default. So it goes to the output layer for classification and gives directly the scores, and we can apply softmax to get the probabilities for each class. So now coming to the next topic of class imbalance. So we have talked a lot about algorithms, but now we need to talk about the data itself. One of the most common and dangerous scenarios we will imagine if we are building a fraud detection model here at Amazon, and let's say 99.9% of our transactions are completely legitimate, like most of the transactions are legitimate, right? And only 0.1% are actually fraud. So if I build a completely naive model which just predicts legitimate every time without even looking at the data, what is my accuracy? It's 99.9% of the time correct, right? So in this scenario, our standard accuracy is completely misleading metric, and it makes you look like a genius while your system fails entirely at its actual job. So how do we fix this? So we have two main angles of attack, either fixing the data or fixing the metric. So our data level strategy is fixing the imbalance. So let's look at the data level strategy. So for example, if we do not have enough fraud examples, we can create more of them using an algorithm called SMOT. So SMOT stands for synthetic minority oversampling technique. So SMOT doesn't just duplicate data, it looks at the minority classes, points them, and interpolates between neighbors to generate brand new synthetic examples. On the flip side, if we do random undersampling, we just throw away a massive chunk of our majority class until the classes are balanced. It is incredibly fast, but you are throwing away valuable information. So in practice, we often combine these. We now coming into the algorithm level strategies, we fix this by penalizing mistakes. So if we do not want to alter the data, we can change how the algorithm learns. The simplest way is to pass class weights equal to balanced into your model. So under the hood, this applies a neat piece of math to calculate weight. So your weight WK will be n divided by k times nk. So this formula ensures that the weight of the class goes up the number of samples in the class. So if your number of samples in the class nk goes down, your weight of the class goes up. So it forces the model to fairly and pay heavily for getting the rare classes wrong. And you can also use focal loss. So originally popularized in computer vision, this function dynamically weights down the easy examples where the model is already confident, and it forcing it to focus all its learning capacity on the hard minority classes. Now, when to use what? So here is your playbook. When do you use what? So if your imbalance is mild, let's say an 80-20 split between the classes, then do not overcomplicate the things. Just use class weights. But if you are dealing with a severe, let's say 99 is to 1 split between the classes, that's when you bring in the heavy artillery SMOT combined with undersampling of the majority class. And no matter which strategy you choose, completely avoid plain accuracy from your vocabulary. And when evaluating these models, you must evaluate using matrices. So you can use something like F1 score, precision recall, AUC curves. These are the metrics that tells you if your model is actually finding the needle in the haystack. All right, so we know which metrics to use, but there is still a glaring problem with how we normally train models. So if you just take your data set and randomly chop it into one training set and one testing set, how do you know you did not just get a lucky split? Maybe all the easy examples ended up in your test set and your model looks amazing, but it will immediately crash in production, right? So to prove that our model is actually robust, we need a better validation strategy, and this is where k-fold cross validation comes in. So k-fold cross validation is a rotation strategy. So the idea here is simple but powerful. Instead of splitting our data once, we divide our entire data set into k equal chunks or folds. So if k is 5, we have 5 chunks. We train our model on 5 of those chunks and use the one remaining chunk as our validation set. Then we rotate, and then we repeat this process 5 times so that every single chunk gets to play the role of our validation set exactly once. So you can see in this picture, we have 5 chunks and we have 5 iterations, and our final score is just the average across all 5 runs. So now you will constantly see debates about whether to use k equal to 5 or k equal to 10. So here is the industry standard. Using 5 folds is absolute standard. It is fast, though it has slight pessimistic bias because you are only training on 80% of your data at a time. If you use 10 folds, your training data is more. You are using on 90% of your data, so your bias drops. But you just doubled your compute time because you have to train 10 separate models, right? So there will be 10 into 10 training. So my rule of thumb is stick to 5 folds unless your data set is tiny. Next is stratified k-fold. So this is about protecting the imbalanced data. Now let's tie this back to fraud detection problem we just talked about. So if only 1% of your data is fraud and we randomly chop off the data set into 5 chunks, a pure statistical bad luck might result in one of those chunks having absolutely zero fraud cases in it. So if that chunks become our validation set, our evaluation is completely broken and useless. So this is why we use stratified k-fold. Stratified just means that algorithm looks at your classification distribution if you are dealing with imbalanced data. Stratified k-fold is not optional, it is absolute essential. And luckily, if you are coding in Python, the creators of scikit-learn already knows this. So if you pass a classification task into their cross-val score function, it automatically defaults to using stratified k-fold under the hood. Now coming to the next algorithm, pushing k to the absolute limit. So we just classified splitting our data into 5 or 10 folds. But what happens if we take that logic to absolute extreme? That brings us to leave one out cross validation, also known as LOOCV. So in LOOCV, we just set k is equal to n. That means n is the total number of data points in your entire data set. So this means if you have 1,000 rows of data, you are going to train 1,000 separate models. Every single model trains on 999 examples and uses exactly one left out example as its test set. So why would anyone do this? But there is a massive catch. First, the variance of that estimate can actually be quite high because you just have one sample. Second, it is computationally brutal. In the real world, you only ever pull LOCV out of your toolbox if you are working with a very small microscopic data set. Let's say n is less than 100. So every single data point is too precious to hold back in a standard valuation fold. Another caveat is the time series caveat. So no time travel is allowed. So now I want everyone to close attention because making this mistake will completely ruin the model. So if your data has a temporal element, so if time matters, you must throw standard randomized k-fold cross validation out of the window. In day-to-day work at Amazon, dealing with sequences of events and temporal data is a constant reality. So if you randomly shuffle your rows, you might accidentally train your model on data from Friday to predict what happened on Tuesday. So if you're essentially giving your model a time machine, it allows the future to leak into the past, right? So giving you an artificially perfect validation score that will instantly collapse the moment you deploy it into the real world. So the solution here is respecting the error of time. So how do we evaluate temporal data safely? We use an expanding window technique. So which is a scikit-learn, which in scikit-learn is called time series split. So instead of randomizing, this method respects the chronological order. And in fold 1, you might train on January and test on February. But in fold 2, you will expand the window. So your train will be you will train on January and February and test on March. You are forcing the model to. Now coming to the next topic of hyperparameter tuning. So up to this point, we have talked about how algorithms learn from data. But there is a whole separate category of settings that the algorithm cannot learn on its own. Those are called hyperparameters. These are like the control knobs. So think of hyperparameters as the control knobs on a machine, and you as the ML engineer have to set these knobs first before the training ever even begins. So you have already seen a few of these today, the learning rate in boosting, the max depth of a tree, or the number of trees and estimators. So finding the perfect combination of these knobs is an art form, and we have three main ways to do it. So the first one is grid search, which is the brute force method. So the most obvious this is most obvious approach. You give it a list of values for each hyperparameter, and it exhaustively tries every single possible combinations. So it is simply too slow for most real world applications. Next one is random search. So it is a smarter baseline. So because of that cost, the industry quickly moved to random search. Instead of trying every combination, what we do is you define a statistical distribution for each parameter and the algorithm just pulls random samples out of it. Now you might think, isn't random guessing worse? Surprisingly, no. There is a famous paper by Gestra and Bengio showing that if you just run 60 random trials, you have 95% mathematical probability of finding a configuration that sits in the top 5% of all possible combinations. So for the exact same compute budget, random search will almost always beat grid search. So here the technique is, what if every single training run takes days or costs thousands of dollars? So that is when we use Bayesian optimization. So for example, in large language models or heavy NLP systems, compute is incredibly expensive. So instead of guessing, it builds a surrogate model, often a Gaussian process that observes the results of previous trials and actively learns the shape of your objective function. It then intelligently predicts exactly which set of hyperparameters it should test next to get the biggest improvement. So if you are using AWS SageMaker or alongside tools like Optuna, so they under the hood beautifully does this. Now coming to the practical tips. First, not all hyperparameters are created equal. So if you are tuning a boosting model, spend most of your time on learning rate. That will give you the best return on investment, followed by max depth, and then finally an estimators. Do not waste compute tuning things that barely move the needle. Second, combine your tuning with early stopping. So if you use something like halving random search, CVINS, sklearn, it will aggressively kill off bad configurations after just a few pokes. So you don't waste time fully training them. Now, coming to the next topic of model selection strategies, we have covered a massive amount of ground for supervised learning, from decision trees to random forest to gradient boosting. At this point, you might be waiting for me to tell which algorithm is the definitive best, right? But here is the hard truth of machine learning. There is a concept called no free lunch theorem. In simple terms, it mathematically proves that no single algorithm will perfectly solve every problem. So you must always compare multiple model families, and you can never assume anyone as best. Now, coming to the workflow, to do the comparison fairly, you need a bulletproof workflow, which looks like this. First, you define a diverse set of candidate models. Second, you tune each of them using cross-validation exclusively on your training data. Third, you take the best version of each model and compare them head-to-head on a separate validation set. And finally, step four, and please, if you remember anything, remember this. You run your absolute final winner on the test set exactly once. If you look at your test set, decide you do not like the score and go back to tune your model again, you are cheating. So your model ideally should not have seen the test set more than once. Because if you do so, you have leaked test set into your training process, your selection process, and your model will fail in the real world. So this is called a selection bias. So to avoid selection bias, you have to just pass it once. And your selection criteria should be beyond accuracy. So it should be how do we actually pick that winner? So in college, you usually just pick the model with the best accuracy, but in industry, it is rarely that simple. So when we evaluate candidate models, here, let's say at Amazon, we have to look at the whole picture. We look at the exact business relevant metric. We look closely at computational cost, not just how long it takes to train, but also the inference latency on the real time. If your model takes 5 seconds to predict a product recommendation, the customer has already left the page, right? So we also have to consider interpretability requirements for regulatory reasons, and how robust the model is to concept drift. If user behavior changes slightly next month, will the model gracefully adapt? So or will it completely break? So all of these things should be taken into account. So because simple model, so even though we spend a lot of time researching and building complex models, you can compromise that simple model generalize better to unseen data. And more importantly, when a system inevitably breaks at odd time, a simple model is infinitely easier to debug, fix, and maintain. Coming to the next module, we have probability calibration and the hands-on demo of scikit-learn. So We have spent a lot of time talking about how to get your models to make the right predictions. But when you are building prediction systems into the production teams, we often run into a very subtle yet critical issue. Just because a machine learning model outputs a number between 0 and 1, it doesn't mean the number an actual probability on the real ground. So take a random forest, for example. If it outputs a 0.7, what does that mean? That just means 70% of the trees voted yes. It doesn't mean the probability to be 0.7, right? So it naturally pushes work predictions toward a middle 0.5 because it's an average of the crowd. And on the other hand, support vector machines, they're even worse in this regard because they just output raw distances from the decision boundary from the support vectors. So if you hand those raw scores to a business stakeholder and call them probabilities, you are going to trouble. So we define calibration as 80-100 rule. So what does this mean to be truly calibrated? So exactly what it sounds like in plain English. If your model looks at 100 different data points and say, I am 80% confident that this belongs to positive class, then exactly 80% of them should be positive. So let's look at this reliability diagram given on the right. The x-axis is what the model predicted, and the y-axis is actual real-world frequency. If your model predicts 0.4, the actual frequency is 0.4. But look at the red line, our uncalibrated random forest. On the left side, it's underconfident. It predicts very low probability, but the actual fraction of positives are much higher. On the right side, it becomes overconfident. It's predicting 0.9, but the reality is only 0.7. So if you use this model to set financial thresholds or risk tolerances, you're going to be completely off base. So the fix is plate scaling and isotonic regressions. So these are two methods. So the first is plate scaling. This is wonderfully simple. If you take the raw messy scores coming out of your uncalibrated model and you literally just fit a standard logistic regression on top of them, it applies a smooth sigmoid curve that mathematically courses those raw scores into a much better approximation of true probabilities. The second method is isotonic regression. So instead of forcing a specific curve, this is non-parametric method. So it fits a flexible stepwise function to your data. Because it's so flexible, it usually gives you a tighter calibration, which you can see as the green line perfectly hugging the diagonal, almost perfectly hugging the diagonal in our chart. So, but it requires a significantly larger amount of validation data to prevent it from overfitting. To wrap this up, whenever you deploy a model where the cost of a mistake matters, whether this is predicting delivery delays, flagging fraud, or managing inventory, you cannot just rely on rank ordering. You just need expected value calculations, and you have to calibrate your model to the probabilities. So now, how do we measure this? So we know what a poorly calibrated model looks like, and how we know how we can fix it using the algorithms like flat scaling or isotonic regression. But in machine learning, if you cannot measure it, you cannot improve it. So let's look at the evaluation sections. So we do not use accuracy for this. We use two specific metrics. The first one and the most popularly used one is Brier score. So let's look at its formula. This is 1 by n summation of p hat minus yi squared, and if it is lower it is better, and if it is 0 it is perfect. So because it's an error metric, lower is better. So if you look closely, you will recognize it's simply the mean square error, but instead of the normal MSE, it is applied to predict probabilities versus the actual outcomes. So the second metric is expected calibration error, or ECE. To calculate this, you divide your prediction into buckets or bin. Let's say bin of size 0.1. So it will be 0.9 to 1, 0.8 to 0.91, 0.7 to 0.8, like that. And so ECE is a metric used to measure the calibration of a model's probabilistic prediction. It quantifies how well the predicted probabilities align with the actual correct outcomes. So to calculate ECE, the predictions are first sorted, then split into m equally spaced bins based on their confidence scores, and then we take the absolute difference between the true accuracy and the average confidence for each bin, multiply it with the size of the bin relative to the whole dataset. So likewise in ECE also, 0 means the model is perfectly calibrated, and higher the number, the more worse the calibration is. Now, when to calibrate and when to skip it. So let's talk about the reality. So you must calibrate when you have downstream business decisions depend on the actual magnitude of the probability. Think about ad bidding or setting insurance premiums or financial risk proxy, which is called risk pricing. So if an algorithm says that there is a 5% chance of an user clicking an ad versus a 10% chance that dictates exactly how many dollars we bid, in those cases, you always calibrate after training SVMs, random forest, or boosted ensembles. But we don't care about the internal score or the internal raw values. So we just care about the ranking. So if the internal score is 0.9 or 0.4, as long as the best product has the highest score, it is fine. So in scikit-learn, it is very easy. If you are thinking to calibrate, you simply import calibrated classifier CV. You pass it in your training base model. Tell it whether you want to use the sigmoid method for plot scaling or isotonic for isotonic regression, and then you can set up your cross validation folds, and it wraps your model. So to close this topic, here is the rule of thumb. Whenever your business logic relies on absolute probability values rather than just a rank list, you must calibrate. So moving on to the last topic of this module, which is about hands-on scikit-learn. So let us switch to the Jupyter notebook with the hands-on code. So welcome to the hands-on portion of supervised learning part 3. In this demo, we are going to take a look at the real world dataset, and we will apply all the learnings that we got from the slides. So this is about a real world dataset for predicting whether a university student will graduate, drop out, or remain enrolled. And we will walk through every major concept we got from the slides: decision trees, ensembles, multi-class strategies, class imbalance, handling, then cross-validation methods, hyperparameter tuning, modeling selection, probability calibration. And finally, we will also see the production style pipeline from the scikit-learn pipeline package. So the dataset has about 4,400 students. So let's so first we have to set up the standard ML toolkit. We will import NumPy, Pandas, Matplotlib. It will take a little. So once done, it will print the versions, right? And we have set the random seed as 42 for reproducibility. We set it to an arbitrary number so that next time when it runs, it doesn't pick a random value. It picks value generated from the seed. And we have applied this dark color, which is just for cosmetic purpose because this is dark theme. So we want the Matplotlib to be dark background. So we want the output to be clean throughout the notebook. So let's load the dataset. So we are pulling the dataset directly from the UCL repo using the UCIML repo package. So X will hold the 36 feature, Y will hold the target level, and so this dataset is about 4,400 students, which is described by 36 features, and it comes from the UCI machine learning repository. So once this is done, it has been loaded. So now you can see that look at the shape. It has 4,424 rows, 36 columns. So these are our features, and we are using the final level as our target level. So look at the shape. It has so each row here is one student. The first few rows: marital status, application mode, course, also macroeconomic indicators like GDP, unemployed rate, and some of are clearly categorical, like integer. So some of them are categorical integer coded and some are continuous. So, and one thing to note is that this is a multi-class classification problem. So it has three classes, which is more interesting than binary because we can discuss OVR, OVO, and softmax strategies, which we discussed. So before modeling, we always do exploratory data analysis. So it is done. So there are two things to highlight here. First is target distribution. So you can see graduate dominates, it's nearly 50%, dropout are 32%, but enrolled are the minority. They are. And about feature types, we split features into 18 categorical and 18 numeric features. So it has total 36 features. The categorical ones are already integer coded. For example, course equal to 171, things like that. And we mark them as pandas category D type. So the downstream encoders will know how to handle them. And also note zero missing values. That's convenient but rare. So key intuition is that all we have to always understand the data before jumping into algorithms, and we have to know about the class imbalance and the feature type that should dictate our preprocessing choices. Then let's do the trend test split. So we followed the standard 80-20 split. You can see test size as 0.02. So but with stratify equal to y. What does this do? It ensures that each split has approximately the same class proportion as the full data set. So without stratification, your test set could randomly have very few enrolled students, making evaluation unreliable. So if you look at the printed ratios here, so so the trend and test both mirror the same distribution, 50, 32, 18, around that. So this matters even more when your minority class is small. Here it is not very much small. 18% is a good number. Now let's go to the modeling. So we start with a basic decision tree. So let's train the tree. It is fast because it was just one tree. So so these are the train and test accuracy. You can see that there is a gap. So this is likely an overfit. Let's plot the top three levels. So here we have plotted just the three levels. Notice the root splits. So you can see the academic performance is the strongest, right? And features like GDP or nationality, they are not contributing. They contribute almost nothing. And you can also see the Gini, intuition, Gini, impurity. So this is the interpretability advantage. Uh, from interpretability, we can also see feature importance. So scikit-learn gives us a feature importance derived from how much each feature. Second semester grades dominate, and so this shows that academic performance is the strongest, and features like GDP and all, they contribute nothing. And this is a one demo to demonstrate the Gini intuition to show how it varies. So you can see we already discussed in the slide that 0 is for pure. When classes are equally balanced, it is at peak of 0.15 for binary. And so this cell just is one demo to see this. So this decision tree we did was overfitting, right? So we did not do any pruning at that time. So we have two knobs from the deck. We have pre-pruning and we have post-pruning. So let's do pre-pruning steps. So yeah, so here we can see that we have limited max depth at the training time. So we see depth from 1 to 20, and then we are plotting trend and test accuracies. So we see that the test accuracy plateaus at around depth 6 to 8, and while the trend accuracy keeps climbing. So the gap between the two curves is the overfitting gap. And let's also do the cost complexity pruning, which is CCP. So here you can see that so we train the full tree, then we progressively cutting the branches that contribute least to the accuracy. So scikit-learn gives CCP alpha path. So higher alpha means we are more aggressively pruning. So here also the key takeaway is that a single tree is interpretable but has high variance. So we tame variance with ensembles. So which we are doing in the next step. We are starting with bagging. So this will take more time than single decision tree because it requires many parallel trees to be trained. So it trains many trees on different random subsets of the data, and this actually reduces variance. So random forest will go one step further, and it will also split one. It will also at each step it will also consider the random subset of features, right? So we had did max feature equal to square root, and then let's compare. So the feature importance comparison is showing that the random forest is spreading the importance more evenly. So it doesn't rely on single dominant feature the way a single tree does. Okay, now let's go to boosting. It will also require more time as well because it's more. It's even taking more time because it's sequential. So instead of parallel trees, we are building trees sequentially, and each new tree is focusing on the mistakes of the previous ensemble. So we have three methods: AdaBoost, gradient boosting, and the result of the third one is, yeah. So it is now here Heist gradient boosting. So so you can see that the gradient boosting and Heist variant typically win usually on accuracy, but they can actually overfit if you have too many estimators with high learning rate. So the results have come. So you can see the trade-off more visually. Then coming to this comparison. So here what we are doing is that we are running a control experiment. We are where we are injecting the label noise randomly to so that it randomly flips some labels and measure. We are trying to measure how much each method is affected, how much each method degrades. So it's running, and the key insight is that the bagging or random forest will be more robust to noise because the noisy samples that are there, they get diluted across many bootstrap samples. On the other hand, boosting will be more sensitive because it deliberately focuses on hard examples, and the noisy levels that we inject are actually the hard examples. So you can see bagging is more robust. Here is the result. Then coming to our next step that we discussed was multi-class strategy. So because our data set already has three classes, so this is a good example to see. So then we have to use OVR, OVO, and these strategies. Okay, then the next thing we discussed was about class imbalance problem. So remember, our minority class was only 18%. It was about enrolled class. So a model can get 82% accuracy just by ignoring it. So that's why we are using both the methods, method of class weight balanced and the method of smooth. So in class weight balanced, it tells the model to penalize mistakes on rare classes more heavily. On smooth, we do oversampling technique. So it generates synthetic training examples of the minority class so that it no longer remains that much minority. So a key so there is also a bar chart here. So yeah, so here is the bar chart. So we compare the vanilla random forest with both these strategies, balanced weight and smooth. So the metric to watch is the minority class F1 or balanced accuracy, not the raw accuracy, because in raw accuracy all are almost same. The same thing is in the bar chart, so it makes clear that the balanced accuracy and the enrolled class F1 is improving substantially with class weight or smooth, even if over So we are running fivefold and stratified fivefold on our random forest, and we are comparing. So we can see stratified will give lower variance across folds because each fold has a representative sample of all classes. That's why it's better. Next technique we learned was about hyperparameter tuning. So every model has knobs, max depth, and estimators, learning rate. So how do we pick the best value? So we had techniques like grid search CV, randomized search CV. So so both uses actually cross validation internally, and they pick the best combo. So it's printing the combo. Um, in the code we pass the parameter grid and let the grid search CV find the optimal random forest. So these are where the best combo that the model found. Then we are doing model selection. So remember the no free lunch theorem, that there is no single algorithm for every problem which is best. So we try different model families and compare and then pick the best. And out of so there is another key principle of Osham's razor, that among the model with similar performance, which we prefer the simpler one, because simpler models are easier to deploy, debug, monitor, and explain. So we are trying logistic regression, decision tree, random forest, gradient boosting, and here is the result. So whatever is the best model selected, so based on this principle, then to that model we will do probability calibration. So if you remember the theory, we discussed that most models output probabilities are just numbers, they are not calibrated. So we well calibrate it. So if the model says 80% probability of graduate, so that should mean that out of 10, 8 should be 8 of those predictions should be correct. So we had two techniques: plot scaling for sigmoid and isotonic regression, which is non-parametric step function, more flexible. So we wrap our best model into calibrated classification, and we can use Breyer score and EC for the selection, right? The next and the final part of this hands-on is about this pipeline. So in production we never let it run. So so in production we never run pre-processing and modeling in separate steps. So that's the error prone. So in scikit-learn pipeline plus column transformer, it will let you chain everything into one single object that can be fit, cross validated, and deployed as a single unit. So this pipeline will do what? It will do column transformation. So it has one hot encoder for categorical feature, and it has standard scaling for numerical feature that automatically does that. Then it will have classifier which will pick the best classifier. So this is about the model part. So we are using hist gradient boosting classifier with random state as 42. Then it has grid search CV, so it will tune the hyperparameter inside the pipeline. And so we have dumped it up in as student dropout model .pkl. So if you are using the same Python version and pandas and numpy version, we can import it back and we can use it in for inference in the pipeline. So this is the code snippet for pipeline. So to summarize why pipelines, so this is ultimate defense against data leakage also. So what exactly is pipeline? It's simply a way to encapsulate all your pre-processing steps and your final model into one single unified object. But the real superpower of a pipeline isn't just it looks clean, it is your ultimate defense against data leakage as well. So remember our conversation about cross-validation. If you manually scale your entire dataset before you split it into k folds, you have just leaked information about the test folds into your training data. So a pipeline automatically prevents this. When you pass a pipeline into a cross validation function, it guarantees that your transformers, like your scalars, are only fitted on the training folds of that specific split. It is foolproof. So a real world data might have mixed data type. So in those cases, it is compulsory that you use column transformer so that it handles well. So the key takeaways from this module is that uh, decision tree are intuitive, but they overfit easily. So we have to always prune our ensemble while using single decision trees. For ensembling, we have bagging, which reduces variance, as well as this is very robust to noises, as we saw in this notebook. Boosting reduces bias, but it is best on clean data. Then we have to use multi-class classifiers for when we have multiple classes. So tree handles it natively, but for binary classifiers like SBM or logistic regression, we have to use techniques like UVR or OVO. We also have to take care of class imbalance. Never rely on raw accuracy. We have to use balance metrics or use techniques like class weight or smooth to better tune our algorithms. Then we have the techniques of cross validation, which always stratify for classification, gives reliable performance estimates. Then we have the technique of hyperparameter tuning, which is a grid search for smaller grids, randomized search for large ones, because um, uh, randomized search when we need faster results. Model selection, we always have to compare multiple models because of the no free lunch theorem, and we have to prefer the simpler ones when the performance of two models are similar. Then we have calibration, which is very crucial when downstream decisions depend on the predicted probability values. And always use a pipeline package. So we have column transformer, pipeline, search CV. So these are for production ready ML pipelines. These are package which wraps all steps into one deployable object, and we can use. So that's the complete supervised learning workflow from raw data to a calibrated tuning. So it's almost always a best practice to use pipeline functionality from scikit-learn library. With this, this module ends. Thank you for attending this session.